Now we're going to work through a few more example problems on practicing balancing chemical equations to hopefully maybe reinforce that skill a little bit more. We will be I'll be setting up inventories underneath my reaction equations so we can keep a tally of how many of each reactant and how many of each product we have. That is not something that is required, but I'm assuming if you are watching this video, you are probably needing a little bit more guided assistance from me, so I will be utilizing the inventory and explaining things very, very, very in depth for those of us who are strugglers for balancing, which is me too. So no worries about that. Okay, so we are going to zoom in, and I thought it would also just be a great exercise for us to write down what type of reaction it is, looking at my couples and single people. So specifically for this first one, I got single calcium, single oxygen. I made calcium oxide. That is a formation of a couple. This is a synthesis reaction, so I will abbreviate synthesis as S. All right, so we're going to keep an inventory, right? My inventory, I have calcium. I have oxygen. 1 calcium on this side. 1 calcium on the product side. My oxygens, I got 2 oxygens on the reactant side and 1 oxygen on the product side, right? Okay, so I see clearly the oxygens on my issue so far. I can get 2 oxygens on the product side if I put a 2 in front of my calcium oxide. That gives me 2 oxygen. It also changes the number of calciums to 2, but I can fix that by putting on the reactant side in front of calcium a 2. I go back to my inventory and adjust it accordingly. It looks like I have the same number of each element on both sides of my reaction. I have balanced this chemical equation. And once again, the reason why we even balance is because we want our equations to actually satisfy the law of conservation of mass by not saying, oh, it's totally fine that an oxygen just kind of just disappeared. That cannot happen. I have to retain that mass, which means the number has to be the same on each side. All right, next one down. What type of reaction am I? I've got a couple. I've got copper 1 oxide. You're like, why is she saying 1? Remember, I reverse crisscross. There is a charge of a +1 on that copper to match that charge of that -2 on that oxygen. I feel like I'm talking too much about that. There's a couple between copper and oxygen. When we write our own chemical equations, we'll real focus in on the naming and writing formulas again. But anyway, a couple and a single carbon. Now I have a single copper and a new couple here between carbon and oxygen. Okay, so somebody has been replaced. This is a single replacement reaction. So an SR, single replacement reaction. Set up our inventory. We have copper, we have oxygen, and we have carbon. Those are the only 3 elements in this chemical reaction equation. Set up my inventory. 2 coppers on the reactant side, 1 copper on the product side. I've got 1 oxygen on the reactant side and 2 oxygens on the product side. 1 carbon on the reactant side and 1 carbon on the product side. So who do we want to start with? Let's just go down the line. Let's see if we can fix the copper situation. Remember, we do not change anything in the inventory first. We put coefficients in my blanks and then we adjust the inventory. The inventory just shows us the effect of any coefficients I've added. Okay, so to get 2 coppers on the product side, that means I need to put a 2 there. Yay, that looks good for me. I'm real excited about that. Now let's see, I've got 2 oxygens on the product side and only 1 on the reactant side. So how about I adjust that by putting a 2 there? Yeah? Yeah, that totally gives me 2 oxygens. But what did I mess up now? 2 times 2, right? I multiplied the coefficient by the subscript. That gives me 4. And you were like, oh my gosh, that is not a big deal. You know what? We may not have run into this having to change my coefficient situation had I maybe started with balancing my oxygen, but that's okay. We can adjust. We can do hard things, you guys. So I can erase my original coefficient and be like, oh, just kidding. Can I now maybe get some 4 coppers on the product side? And you can't if you put a 4 or change that coefficient to a 4. So now are we looking like we are good and balanced? I feel pretty good about that. That was amazing. All right, we are ready to move on to number 3. Let's identify the type of reaction. I have a single person and I have a couple and I have now a new couple. You were like, what is going on? I was anticipating something. I will probably give y'all examples of types of reactions that you will not have to write the products yourself. But any reaction technically where I have more than one thing coming together to make just one product is a form of a synthesis reaction. Now, those two things that are coming together are not two pure single people, so it does not follow our Taylor Swift and Travis Kelce coming together to make a couple situation. But I have synthesized one product by forcing or reacting two or more things together. That was a tangent to say that this is a synthesis. I can identify that when I see more than one thing on the reactant side and just one thing on the product side. I've synthesized something new. Okay. So now we are ready to set up our inventory. We have an oxygen, we have a potassium, and we have a chlorine in this. Cool. 2 oxygens on the reactant side, 3 oxygens on the product side, 1 potassium on the reactant side, 1 potassium on the product side, 1 chlorine on the reactant side and 1 on the product side. I feel like I'm going to get my tongue twisted by saying reactants and products and probably mess that up a little bit. And I am sorry. I'm trying my best. Aren't we all trying our best? Okay. Do you remember from our notes page when I said even, odd, double the odds? Specifically when we have an even, odd situation with numbers that do not involve 1. What I'm going to do here is I've got 3, which is an odd number of oxygens on the product side, and 2, which is an even number of oxygens on the reactant side. I'm going to start off by doubling the side where the oxygens are odd, meaning on the product side, and seeing if that kind of kickstarts me in the right direction. So I'm going to put a 2 there, right? Yeah, that gives me now 2 times 3 oxygens, 6. It also adjusts my potassiums over here to being a 2 and my chlorines being a 2. Okay, that seems kind of wackadoo that I started off with doing this, but now look how much of an easy adjustment it is over here to fix everybody else on the reactant side. To get my 2 potassiums over here and my 2 chlorines, well, let's start with the oxygen. I don't know why I didn't start with that. Can I get 6 oxygens over here by putting a 3 coefficient in front of O2? Yup. Oxygens balance, and watch how quickly I can balance both my potassiums and my chlorines. I can put a 2 in front of potassium chloride, and that makes my inventory look so good, look so nice. Okay, so that's my even, odd, double the odd. And once again, guys, these rules are not like absolutes. Like sometimes you may run into a chemical equation, you're like, your even, odd did not work, and it's like, well, I am just giving any sort of suggestions to maybe help out in some way for those of us who really struggle with balancing and it does not just appear to us naturally. All right, let's do the next one. Number 4. Let's see what type of reaction I have. I have a couple, nitrogen and hydrogen. This is ammonia. And I have a single person, yes? And it looks like over here on the product side, I have a new and different couple and a new single person. So this is a single replacement reaction. Yep. Okay, set up my inventory. The elements that I have are nitrogen, hydrogen, and iodine. I got 1 nitrogen over here, 1 nitrogen over there, 3 hydrogens over here, 2 hydrogens over here, 2 iodines over here, 3 iodines over here. See, I've just started saying over here, and not reactants and products side, so I hope you guys are kind of with me. Wow, I see a couple situations of even, odd. Maybe we'll pick one of the hydrogens and one of the iodines and get started with even, odd, double the odd. Let's check out hydrogen first. Hydrogen is odd on the reactant side, so I'm going to double hydrogen on the reactant side by putting a 2 in front of NH3, in front of ammonia. That gives me now total 6 hydrogens, and it gives me 2 nitrogens. Okay? Well, I can fix some things. Let's start by fixing the thing that we started off trying to fix by doubling. Let's fix the hydrogens and see if we can get him to also be 6 on the product side by placing a 3 in front of H2. All right, let's maybe fix my nitrogens. Can I get 2 nitrogens on the product side? Yeah, by putting a 2 there. That gives me 2 nitrogens. It also, 2 times 3 gives me 6 iodines, which, oh, look at this. Look what's about to happen here. I've got 3 there in front of my I2 or my iodine to make a total of 6. Okay, so I think this is one of the first examples. Now, the example before had numbers in each and every blank. One thing I want you to check is if you've put numbers in all of your blanks on a reaction equation, check to make sure the ratio is the lowest possible. Some of y'all may do some balancing things and adding coefficients, and if this was a 4, 6, 4, 6, you're going to have to reduce those ratios back down to this lowest possible ratio, okay? So it's something just to keep in mind there. All right, moving on. We've got number 5, practice problem number 5. Let's see what type of reaction this is. Oh my gosh, I see some polyatomic ions. That is cool. We know a polyatomic ion is just acting like one thing or one person in a couple. I'm glad they already have parentheses around them because we know it is a useful skill for us to keep those polyatomic ions intact in my inventory to help me with my balancing. It's also going to help me name the type of reaction. I got a couple between copper and phosphorus or phosphate. And I got a new couple between zinc and phosphate to make a single copper kicked out. This is another single replacement reaction. Okay, so looking here, my inventory that I'm setting up, I have zinc, I have copper, and I have phosphate. And it feels criminal to not put the -3 charge of the phosphate ion, but I find that to be maybe a little bit confusing since we are already putting numbers here, but you get what I'm saying. That phosphate, he is a charged ion. He is not just by himself. Okay, so we're counting now. We got 1 zinc here. We got 3 zincs here. We got for copper 3 here, and we got 1 here. For my phosphate, we have 2 total here. Once again, I'm looking at if there's a number behind the parentheses. And I got a 2 total here. Okay, so let's see. Let's start with the first one, zinc. We got an issue with zinc. We would like to have 3 zincs on the reactant side to match the product side. How about we do that? Okay, that now gives me 3 and 3. Looks good. The only other thing I have an issue with is copper. I would like 3 of him on the product. Oh, look at this. Look how, oh, and everybody be good. This looks so nice. So some of them are kind of easy like that. But the parentheses around my polyatomics it is an absolute game changer, you guys. So I cannot stress that enough. It cannot, just keeping those parentheses there to help you in all of the ways. Okay, so let's go to the next one. Let's see what type of reaction I have here on problem number 6. Looks like I got a couple between tin and chlorine, and another different couple between chromium and nitrate. And then over here I have a different couple between tin and nitrate and chromium and chlorine. It looks like I've got a double replacement reaction here where we have swapped partners, which is super exciting. So a double replacement reaction. I also love that they totally have that nitrate in parentheses because I know it's going to make things a heck of a lot easier when I'm trying to balance. So I set up my inventory. I have tin, I have chlorine, I have chromium, I have nitrate. So setting up how many on each side? 1 tin over here, 1 tin over here, 4 chlorines over here, I lost my chlorine. 3 chlorines over here, 1 chromium on the reactant side, 1 on the product side, and then my nitrates I have 3 and 4. When I start getting bigger numbers like this, and these big numbers are coming from, thank you, Transition Metal 10, who's got a +4 charge, I start getting a little bit swirly, and I'm going to anticipate having maybe some bigger coefficients than I would usually see, or bigger numbers of each atom on each side. I know this is an even-odd situation, but that even number is a bigger number than the odd number here, and if I were to double the chlorines, I would be getting a 6, and then I'm dealing with a 6-4 situation, and it just turns into a big spill over here. So what I'm actually going to do is I'm going to see if I can get both the 3 and the 4 maybe to be the same by making them be 12 in some way, right? That seems like maybe an easy fix to where if I wanted to, I could multiply 3 by 4 and get a 12, and then I could multiply 4 by a 3 coefficient and get a 12. So let's see if that sets us up for more success. And I know some of you are like, what is she doing here? You'll get used to kind of playing around with putting numbers in, and you may have to erase some things, but just to get us started off, I figured that, maybe we would just kind of think about some other ways that we could get the same number of each element on each side to be the same, and the potential of just like thinking about those numbers being multiplied together in order to get them the same is some place to start also. So for my chlorines, I'm going to come over here and I'm going to put a 4 coefficient in front of where the chlorine was 3. The purpose of that is that's going to change this chlorine on the product side to be a 12. It also changes my chromiums to be a 4. You're like, oh my goodness, this is so annoying. Not a big deal. It'll hopefully all work out, hopefully. So now I'm going to say, okay, well, chlorines, I need to get maybe 12 chlorines on the product side. That's a pretty easy fix because if I put a 3 coefficient, that 3 times 4 will give me 12, right? It messes up my 10 to be 3 over here. Not a big deal. I bet you we can fix maybe some of this stuff. In fact, let's see if we can fix some of this stuff for the 10 right now. I have 3 10s over here. To get 3 10s over here, let's see what happens if I put a 3. I got 3. And how many nitrates do I have here? 3 times 4 total nitrates is a 12. Okay, now the picture is getting a little clearer. To get 12 nitrates over here and to get 4 chromiums over here, how about I put a 4 there? Yes, that will give me 4 chromiums to balance my chromiums. It will also give me 4 times 3 to give me 12 nitrates, okay? So I have numbers in all of the blanks. I got coefficients everywhere. I cannot reduce down that ratio anymore. If this was a 6, that was an 8. This was a 6, that was an 8. That is a multiple ratio of this 3, 4, 3, 4. You would have to reduce it down. Okay, so that's a fun little example. A little bit different, a little bit new, a little bit fun. Okay, let's do this next one. What type of reaction am I? What type of reaction am I? You're like, couples, single people. I love that we are looking for couples and single people, but something else that we always have to just keep our eyes ready for is finding a combustion reaction when I see it. If you see a hydrocarbon, something with carbon and hydrogens in it, and the second reactant is oxygen, and the 2 products are carbon dioxide and water, that is a combustion reaction, okay? So combustion reactions are super fun. They tend to be a little bit, well, they tend to be the most challenging ones to balance. I'm not going to give you crazy challenging combustion reactions here because what we were focused on this page is just getting comfortable with balancing in general. We will practice balancing more combustion reactions when we have a lesson where we specifically talk about and write combustion reactions only. But the process is totally the same. I can totally set up my inventory. I've got carbon and hydrogen and oxygen. And yes, I said we'd spend an entire separate lesson on these combustion reactions, but the main thing to take home on combustion reactions is you do not want to touch oxygen. You do not want to balance him until the very, very end. So we're going to write balance carbon, then hydrogen. Oh, you cannot see. And leave oxygen for last. Okay? And the reason why we're doing that is because, y'all, oxygen is found like in a bunch of different things. So if I try to put coefficients in front of an oxygen, it's gonna mess up a lot of people. Versus my carbons, they're only in one spot on the reactant side and one spot on the product side, and my hydrogens are also in one spot. Oxygen all over the place, which is why we always leave him for last. Okay, so setting up my inventory, I have 3 carbons on the product side and 1 on the reactant side. I've got 8 hydrogens on the product side and 2 on the reactant side. And oxygens, he's only found here in the O2 on the reactant side. So I can just grab that 2 and be like, yep, there are 2 of them on the reactant side. But I've got to make sure I factor in the locations of both of these oxygen representatives, right? I got 2 oxygens coming here from the CO2, and I've got 1 coming from the H2O. So I have to add those together. 2 plus 1 is I have 3. Okay, balance carbon first. Balance carbon first. I got 3 over here, so guess what? I'm going to put a 3 in front of CO2 to give me 3. Going down the list, balance hydrogen next. I have 8 here. How can I get 8 over on the product side? By putting a 4 in front of water, because that will mean 4 times 2 gives you the 8 that you want. We're feeling good. And now the only thing I have left to balance is my oxygens. And what that looks like is I'm going to recount all of the oxygens on the product side, which, y'all, I should have been changing my inventory down here when I balanced carbon and hydrogen, but we will change it now. It's got to recount how the effect of adding these coefficients for my carbons and hydrogens have affected the oxygens on the product side. Meaning, from my carbon dioxide, I have 3 times 2, 6 oxygens now here. And over here on my water, 4 oxygens here. So 6 plus 4, that gives me 10, right? Which means I got to figure out how to get 10 oxygens on the reactant side. There's my only oxygen on the reactant side. To get 10 of him, I will put a 5 there because 5 times 2, the subscript of the 2, gives me 10. So for these combustions, balance carbon first, hydrogen next, leave that oxygen for last. And when we get into it, sometimes our combustion reactions, things will get hairy down here on the oxygens and we will have to make some adjustments, but we will not worry about that just for today. We're going to just be happy with our combustion reactions and knowing that oxygen, we leave him for last. Okay, next one. We have, what type of reaction? Okay, so I see a polyatomic ion of hydrogen, or hydroxide, right? And you're like, great, polyatomic ions, keep them together. But the rule is for my polyatomic ions, when keeping them together in your inventory and balancing them all together, is I can only do that if I see the polyatomic ion intact on both sides of the reaction equation, okay? So what that means is I see hydroxide here. I don't see him. Man, that stinks. Walk away. Here is something really, really unique and cool. Do you see water on the product side? I sure do. There is an option for you to not think about water as H2O, but maybe think about him as an ionic compound or like an acid between hydrogen and hydroxide. You're like, you cannot change things like that. I just moved the letters of the alphabet around. Does that not also have 2 hydrogens and 1 oxygen? Yeah. Okay. And the reason why I did that is because, y'all, look at that. I have hydroxide here and then here. That's something else you will need to notice, though. I do need a separate inventory indicator for the hydrogens that are found outside of my OH, my hydroxide polyatomic ion. But that makes things a lot easier than just blah, like I see lots of hydrogens there. I'm going to be messing up some coefficients and it's going to give me a big headache. So yeah, write water as HOH if you see the polyatomic ion OH on the other side. That's a special, another unique little tip here when it comes to balancing. I'm ready to set up my inventory. Wait, no, I'm not. I'm going to name what type of reaction this is. I got too excited. Okay. Oh, yay. This is good. So I have lead and hydroxide, a couple. I've got hydrogen and chlorine, another couple. Ooh, I bet I know what's going to happen. And thank you for writing HOH because now I can see the switching of that couple a lot better. That lead now pairs up with the chlorine to get lead 2 chloride. And the OH and the hydrogen pair up to get that H2O or the HOH. I've got a double replacement reaction, you guys. How fun for us. Amazing. Okay, let's balance this double replacement reaction by writing an inventory of all 4 of the people involved in this couple swapping. I've got lead, I've got hydroxide, I've got hydrogen outside of my hydroxide, and I've got chlorine. Okay, I got 1 lead over here. I got 1 lead over here. I got 2 hydroxides over here. I got 1 hydroxide over here. I got too excited. I got 1 hydrogen, and I'm meaning hydrogen not found in my OH polyatomic. I have 1 hydrogen, right? Because I've now chosen to written water as HOH, right? So he is 1 hydrogen. The other H from H2O is found in the hydroxide, okay? And then my chlorines, I have 1 on the reactant side, 2 on the product side. Let's see. How about let's just go down the list. Lead, you're good. Hydroxide, let's fix you. I had 2 over here. How about I put a 2 in front of HOH to get 2 of those? It has also changed the hydrogens to be 2. Well, how about I put a 2 in front of HCl to give me 2 hydrogens and my 2 chlorines that I was hoping for on the reactant side. Amazing. We are balanced. We are looking good. I am super excited about that. HOH is fantastic if you see hydroxide on the opposite side. I love that for us. All right, last one. I'm getting super excited, super excited, super excited. What type of reaction am I? Wow, you guys, I see our OH friend again. Oh my gosh, I'm like, is there water on the other side of the reaction equation? There is. Let's see if this maybe makes something of use appear to us for our balancing, and maybe also of use for us to figure out what type of reaction it is. That's a terrible OH, but hopefully you can see. Single sodium, got a single person, and a couple. I got a couple between hydrogen and hydroxide. Yes, we know we're water, but yeah. Looks like they've swapped partners, or it looks like sodium has kicked out the hydrogen to make sodium hydroxide, and here we have hydrogen kicked out by himself. Okay, this is a single replacement reaction. Yes. All right, setting up my inventory. I have sodium. I have hydrogen, yes, and then I have my hydroxides. Okay, we are ready to count how many of each I have on each side. 1 sodium on the reactant side, 1 on the product side, 1 hydrogen outside of OH, 2 hydrogens over on the reactant side or product side. I told you I'm messing it up. It's okay. I got 1 hydroxide here, 1 hydroxide here. So I obviously see an issue of where I need to start this hydrogen situation. So I will be putting a 2 in front of HOH to give me the 2 hydrogens that I would have liked to seen, and that changes my hydroxides to be a 2. No big deal. We can do the hard things. Let's see if we can get 2 hydroxides on the product side by putting a 2 in front of sodium hydroxide. Oh, that does that. It also changes the sodiums. You're like, oh my gosh, there's so much changing happening here, but look how this is about to resolve itself. If I put a 2 in front of sodium on the reactant side, now everyone is balanced. Okay, this is not a ratio that I can reduce down because I ain't got no number there, okay? If this was also a 2 there, then please all of those ratios will reduce down to 1s. But this is the lowest possible whole number ratio that I can have for all of these coefficients, which are 2, 2, 2, and a 1. A 1 will always limit you. So this was a great little lesson in balancing, a great lesson in reinforcing those polyatomics in parentheses, right? Introducing these combustion reactions here and realizing that oxygen is always going to be a disaster for you, so it is best to leave him last for balancing. And we introduced this really new fun technique of being able to write water as HOH in a lot of ways, especially when we're considering him as maybe a couple that could be involved in a double replacement or a single replacement reaction. But I hope this gave you guys some tips. Some of these tips may be useful. Some you were like, I do not like that at all. Whatever it is that you can do to put the correct coefficients in front of your reaction equation chemical formulas, that is all that we are looking for. And I hope that we are set off to a little bit more success with that.